Hey everybody, my name's Taylor Moreland. I'm in live group M7. I go to class on Thursday from 3 to 6. Alright, here we go. Okay, introduction. So our objective is to exemplify Newton's second law in action with the effects of gravity and drag. Now, for me, I'm going to do this with our wonderful, and emphasis on the word wonderful, as in not, physics textbook, which I'm going to use as the fast object, and then I'm also using a laminated card for the slow object. Now, before we dive right into this, there are a couple things that we need to make sure we understand before we start. Now, one of those is we must assume that the only forces that the two objects will be affected by is Earth's gravitational pull and later drag for when we do the later models. And also, for the actual experiment, even though there's a small amount of motion in the x direction, we will assume the object only moves in the y direction. Okay, initial conditions for the textbook. Its mass is 1.089 kilograms. Its length is 0.27 meters, and the height at which I placed it at is 2.066 meters. And the time step I made was 0.033 of a second, which overall is very small compared to the total time interval, which is 0.7565 seconds. So that should make our calculations right. Alright, the initial conditions for the laminated card are: for the mass, it's 0.05 kilograms, the length 0.17 meters, the height, it will start off at 0.14 meters above the ground, and the time step is also 0.033 of a second, just because, again, it's really small compared to the total time interval of 0.967 seconds. Alright, so let's first take a look at the tracker video for the textbook. Alright, so as you can see, I've placed the x-axis all the way at the bottom, down here, and the book's up here. So it's going to start from up here and then work its way down. So it's starting at positive y values and working its way down. So let's hit play. Now as you can see, it is slowly dropping, going from rest to eventually accelerating up to 9.8 meters per second. And boom. Stops. Okay, so let's go ahead and take a look at the graph for that. So as you can see, we start initially at rest here, and eventually as it goes from my hand down towards the ground, it eventually starts speeding up, therefore accelerating. So you can see this nice parabolic kind of shape for when you just involve the normal forces in it. Alright, so now let's take a look at the tracker video for the laminated card. Alright, here we go. As you can see, starts up here, works its way down. For this object, again, now it's not like the textbook. It's much less heavier, so it's going to float in the air more. Alright, so that's what it does, and let's take a look at its graph. Now, as you can see, instead of having this nice parabolic shape, we have this kind of straight linear shape, just because it's just kind of with the forces of drag, it's really being opposed by. That's why it takes a lot longer for it to get down. Now, for the models, I have every single model provided and created all of them, but unfortunately, I could never get the data to actually extract from the program for Python. So while I could not have the models actually to display the data from the models compared to the observation data, I still created the models. So back to the PowerPoint. Okay, so what if? Okay, well basically just to sum it up really quickly. In my case, the laminated card would fail to reach terminal velocity, whether there was only a gravitational force acting on it, or in the later cases where you have a drag force acting, because as you can see in my tracker video, the height from which they fall is pretty small, so there's not enough time for it to reach terminal velocity. Okay, now what does all this mean? Okay, the big thing you should take away from all this is that terminal velocity is achieved when the gravitational force equals the drag force. Pure and simple. Alright, that wraps up my video. Thank you for taking the time to watch it, and I hope you have a great day.